flows. And there's kind of two main points here. One is that we've got this sort of consistency between different experiments in terms of we've got these dark areas occurring in the same parts of the bed, which is showing that morphology is very much affecting where the sediment patches are stable. And then the other one is to say, well, actually, if we look at the mean at which that sediment patches are being eroded, there's not that much difference between these experiments, but the mean discharge here is a lot higher, which is again is potentially showing this impact of these sediment patches in sort of developing stable cover and being eroded at a lot higher discharge. Okay, so just going through sort of conclusions quickly. If that's all right, we've got, so basically, the bed induces a spatial pattern of flow, which comes from variable discharge. And the depth and velocity seem to respond differently depending on location. At a point discharge, it looks like a sort of topographic scale of about 150 millimeters may be appropriate, but it's quite sort of uncertain. But actually, maybe this sort of approach is actually not unreasonable at a point scale. In terms of sediment cover, again, linear relationship to a first approximation may not be unreasonable. It does seem to develop from low elevations, but clearly flow is also important. And then also, we find that patches do persistently perform in the same locations, which is, again is this function of morphology. But possibly, if we put more sediment volumes into the flume, the role of the topography actually maybe becomes less important, and sort of grain-grain interactions maybe become more important. Cool, thank you.
So, questions, please. This is the intent of... Gary, you are Hello? Okay. Gary, I have no doubt your volume of voice will carry. Please ask your question.
But first, let's see if we can solve the problem.
We can solve the problem.
Could you return to a slide where you showed fruit number audit? It was toward the beginning.
Yeah, that's...
I should look carefully. You did number your slides, which is very kind.
I did,
But
I
I
can't
didn't.
remember which it is either.
There, I think there. So I can't really read the slide, but I guess that your field numbers have fruit numbers, field case have fruit numbers between about 0.2 and 0.5, and your flume numbers are around 1. Am I reading correctly?
Yeah, that's about right, yeah. The flume number always does seem to be stabilizing at about 1.
Okay. Just a logistical question. Is the fruit number of 1 in the laboratory by design, or was it a limitation of the facility? Did you want fruit numbers that high?
We didn't deliberately set the Froude number, so I guess it was something that fell out. I'm just trying to... I mean, I guess the main way it was set up was we used, so the slope was the same slope as in the field, and I guess the tailgate was set up so there wasn't a backwater effect.
Okay. So this is not meant to be a strong criticism, but it's not really a fruit model if the fruit numbers don't match.
The problem is that we don't really know what the Froude number is in the field under those sort of flow conditions.
Well, you've got some dots on the diagram.
At much lower discharge.
At much lower discharge than the flume.
Yeah, sorry, so discharge is on, so the field data only go up to discharge of about 6 Qmax.
Yeah.
And the lowest flume equivalent one is about, sort of bank 4, which is about 10.
Okay. Do you think if your field discharge went that high, they would roughly match?
Potentially, yeah.
Okay. The reason I'm asking the questions is just to try and understand something, is that when the fruit number is sufficiently high, as the flow goes over individual grains, it can modify the water surface, which can change the mobility, I think, in some cases, significantly compared to when the particles are completely submerged. And I wonder if you noticed that going on in the flume, and whether you have any observations on to whether something similar might be happening during floods in the field.
Okay, generally the water depths in the flume were actually sufficiently deep that all the particles are submerged. So I think the sort of depth to grain-size ratio is quite large. Whereas the effect you're talking about seems to be more if you've got like sort of skimming flow over particles. Is that right?
Of course, I'm not sure. It's just that fruit numbers R1, a bump on the bed can create a bump on the water surface too, which can interfere with how the particles move. Maybe it was not very significant, but you would have seen something when you did the experiments.
Yeah, okay. I don't think we noticed that effect. But I guess I can go back and have a look through the images just to see if there are sort of water surface effects.
Okay.
Yeah, cool.
Thank you.
I see a question back. Lady from Switch. No.
Thanks, Rebecca. Very nice experiments. Did you try, or what do you think would happen if you went directly to the higher discharges? Because you've got this inherited bed when you're increasing the discharge, ramping it up. So
Yeah.
What would happen if you went directly to 50?
So we've actually got some exposed. So there were 50 was the highest that we started with in terms of putting sediment mass in. I don't know. So the fact that some of these, where are we? The fact that those sort of yellow, the green and the red lines actually seem to sort of merge onto each other, regardless of the initial amount of sediment which has been put into the bed. So these plots here are basically the same data, just separated out by sediment mass. But you can sort of see that we've got a line here which starts at 20, another experiment here that starts at 35, there's another one down here that starts at 50. And actually starting at different discharges, they actually do seem to, if you put the same mass in at those different discharges, they actually do seem to collapse in some cases to quite a similar trend, which rather suggests that actually maybe there isn't that much of a sort of inherited effect. And actually the bed is actually responding quite quickly to those different flow conditions as that flow is ramping up and changing. So I guess I might argue that maybe under these sort of volumes of sediments, there isn't that much of a sort of inherited effect. Whereas actually maybe when you've got these larger volumes of sediment in up here, clearly that does seem to be a far more stable bed. We're actually not getting such a rapid change in sediment cover. So it seems to be that actually maybe when you've got a lot of sediment in the flume, I think you might be right that that sort of inheritance effect is actually quite important.
More questions? This way. She will pass it.
Hi, you have to excuse me if this question is too basic, but I'm a mathematician doing a PhD in geology.
That's fine.
At what point does the river become a bedrock river? I mean, at what level of coverage? Where do you draw the line?
That's a very sensible question. I think the argument tends to be that at the point at which you've got some sort of bedrock in the channel sort of, I guess if the channel has to erode bedrock and able to move, then some would argue that that's at what point it becomes a bedrock river. So you might have some rivers that kind of are considered to be bedrock rivers, but you might look at and actually might appear to be full of sediment.
Okay.
But in order for the channel to migrate, it's got to erode the bedrock.
But in that case, you're assuming no erosion in your bedrock, so...
So I guess in my case here, yeah, I've just got sort of static bedrock morphology. I guess the aim of these experiments was to kind of look at the dynamics of sediment cover on top of a sort of bedrock surface.
Okay, thank you.
I would like you to return to your movie about the sediment leaving the bottom.
Yeah.
Yeah, I see an instrument there.
Yeah.
And actually you have a patch that is rather stable, right? Near the instrument.
Yeah.
Because then I saw the figures in one of the last slides in which you show actually the figures of these films in which you describe location of patches, etc. Are you sure this instrument is not influencing that location?
Yeah, I agree, it looks like this instrument might be, but actually, if you look at the topography, there's actually a very low area of the bed. just in here. You can sort of see we've got this ridge line along here. There's a low patch in here, and actually that ADV is sitting on a higher area of the bed, the upstream of that. So I'm pretty sure it's that sort of change in topography which is determining that that patch is there. It's actually not the ADV itself.
Okay.
Maybe I didn't get everything, but I was wondering why bothering scaling, because you don't compare with nature, right?
Good question. I guess the point is that quite a lot of bedrock experiments that have been done previously tend to, I guess there tends to be a question about sort of what grain size you should have compared to the size of the channel. And although there's maybe not a direct comparison because we just don't have the comparable data from the field, we wanted to try and create a model that we would have some sort of, I guess we'd have some sort of faith in that it was actually seemed to be operating in a reasonable way compared to what we might expect to find in the field. So although, like I say, we don't have that sort of data from high flow events from Trout Beck to do the direct scaling with, it sort of suggests that this model is actually behaving in a reasonable way and that actually it's not unreasonable to take results from this and think, okay, that might actually be how the real system behaves under those high discharges.
I thought I had over here. Yes.
So correct me if I'm wrong, but you said your field site had about 20% sediment cover. What, in your experiments, how does that compare to the actual sediment cover? And are there any plans to look at where the patches form in the experiments versus in the field?
Yeah, no, that's a very good question. When I initially went to go and survey the bed, I guess I did have vague plans of thinking, well, maybe I can just get rid of the sediment before I scan it. Clearly, that wasn't going to happen, because even 20% cover is a lot of sediment. So you're kind of right that effectively this bed here, so certainly this area part of the bed here, the topography is actually, in areas, is actually the top of the sediment, which is currently in that channel at the moment. And again, some of these lower areas around here are actually full of sediment, or do have sediment in the field. And again, that topography is kind of the top of the sediment. So kind of what we're modelling here is more what would happen in Trout Beck if we added more sediment to it, rather than maybe what kind of that sediment is at the moment. So I have done some comparison between where the location of the sediment is in this model compared to what you see in the field. And actually, they're not dissimilar, but they're not perfectly similar. And I suspect that that's because what we're modelling here is actually slightly different to what we actually see in the field.
Hi, I'm curious, you have such a detailed information about the bed topography, and you use this really simple model to compare, if I just filled up the bed with sediment. Are there more sophisticated ways of doing numerical modeling that you can take advantage of that rich data set? Is that something you considered, and how would you do that?
That's a good question. I think, so the really simple one in terms of just saying we'll just start from the lowest elevation and we'll just fill it up, was to kind of say, okay, if this is purely gravity driven, and that's the only thing that's affecting where sediment cover forms, let's sort of start with the simplest model and see how it compares. I guess in terms of making something slightly more complicated, clearly there's this question about the sediment is being introduced at the top of the flume and it's got to travel down to those locations of the bed. So you could say, okay, well maybe the next thing to do would be to create a model that sort of looks at sediment pathways. And so you could have a model like maybe with sediment sort of moves in steps, and each time it gets to a local low, it gets deposited, and maybe build it up that way. So yeah, you could sort of, I guess, extend it a little bit, or you could sort of go the whole hog and say, okay, I'm going to try and run a CFD model over it, and try and couple that and see how that produces sediment patches. So there's quite a lot of scope for sort of extending that sort of model. I guess it was just curious to say, okay, let's start with a really simple model and see how well that does.
Where's my card? Are there any other questions? Oh, I see one more hand. A lot of discussion, so here's the mic. Are you going to go last? Right.
leading question. What condition does the movie end with?
What conditions it end with?
Yeah, cessation of feeding?
No, so basically we ran the flume up to 70 litres per second,
Okay.
and then this is it was turned off,
Okay.
which
So
is...
watching the movie, it's hard not to see the train of sediment moving on the bottom of the image. Just curious, do you see that in the field, and why is there a preferential pathway there? And does that play any role in patches forming?
What you mean
So you can see the train, the clear pathway of sediment mobility on the very bottom of the image.
what's around here?
No, on the very bottom of the film.
Oh, I see here. Oh,
And it persists through the whole movie.
I guess, to be honest, I think actually quite a lot of that dark bit that you're looking at is actually sort of the entrance with the flume wall and the plastic tiles. So I mean, there is debatably a bit of a wall effect possibly along that part of the channel. But having said that, actually this bit of the river that we're reproducing has quite steep, quite vertical walls, which are about sort of a metre high, which is sort of a combination of till and peat. So actually, obviously they're not smooth as this glass wall, but actually, in terms of shape, they're maybe not that massively dissimilar.
Okay, thank you, Rebecca, very much. That was quite interesting and gets us thinking. I get to ask one last question, which is, will they let you come and dump a bunch of sediment in the river?
If you want to give me a hand getting a wheelbarrow up there to put all the sediment in the river, then...
It would be fun. Okay, thank you very much. I think I've been given permission to do the Gilbert Club thing so that we can get to know each other. We already know this fine man, I'll go this way. Can I ask you to just give your name and your institution?
I'm Helena van Vacht from Applied Geology in TU Delft.
I'm Daniela Bogociu from University of Polytechnics from Bucharest, Romania.
Wes Lauer, Seattle University.
I'm Vania Ferrara, University of Naples.
Massimo Guerrero, University of Bologna, Italy.
Sarah Kelly, Utah State University.
Claire Masteler, UC Santa Cruz.
Rob Ferguson, Durham University, retired.
Hiroshi Niwa, National Institute of Technology, Japan.
Hiroshi Takebayashi, Kyoto University, Japan.
Sean Chartrand, University of British Columbia.
Matteo Saletti from ETH Zurich.
Alessandra Crosato from UNESCO IHE Delft.
Roland Keitner from University of Natural Resources and Life Sciences in Vienna.
Alain King from ISTA France's Grenoble Center.
Benoît Camnen, so from ISTA as well, but in Lyon, France.
Emeline Perret from ISTA in Lyon, France.
Kensuke Naito, University of Illinois.
Michal Zal, also France, although I don't have an accent. University of Aix-Marseille, Serege Laboratory.
Kimberly Hill, University of Minnesota.
Pierre Leval, Ben Gurion University.
Bram Fricket, Antwerp, Belgium.
Andy Wickert, University of Potsdam, Germany.
Sarah Sam, University of Potsdam, Germany.
Stefanie Tevelde, also University of Potsdam.
My name is Suzanne Kwartel. I'm from Rijkswaterstaat, which is a governmental organization in the Netherlands responsible for river management.
Jordan Rieper, independent consultant, watermotion.eu, the Netherlands.
I'm Joel Johnson, University of Texas at Austin.
Thomas Poisson, University of Friend.
Manuel Bogoni from the University of Padova in Italy.
My name is William from RWTH Aachen University in Germany.
My name is Tobias Schroff, also from RWTH Aachen University in Germany.